Hey, BC Calc, we got some day 12 notes on derivatives of trig functions. Some awesome stuff. So we are going to get to a point today where we get to derive the derivatives of each of the 6 trig functions, okay, sine, cos, tan, and their reciprocals. So we'll be getting into that in just a little bit, but just to recall and make sure we're good to go, let's do a quick summary of our derivative rules. You see some functions listed in the left column. Your job would be to write the derivative of those equations in the right column. So hit pause quick, test yourself, make sure you're good with these derivative rules. All right, I'll go through them real quick. So if y equals c, some constant, the derivative, of course, y prime is 0. Here's our power rule, y equals x to the n, the derivative n times x to the n minus 1. We've got constant times a function equals constant times the derivative. We've got the derivative of a sum is equal to the sum of the derivatives. And then we know that that's not true for the product or the quotient, so just make sure you're cautious about that while we're still getting the hang of all this. Right? The derivative of a product equals the derivative of the first times the second plus derivative of the second times the first. Hopefully you're feeling pretty good about product rule at this point. And then finally, our new quotient rule that we have, f of x divided by g of x. Our derivative would be low d high minus high d low over low squared, right? Low g of x d high, derivative of the top minus high d low, and then we got low squared down there. So if you're good with those derivative rules, I'm going to encourage you to try this AP style question. It's a good one. Okay, given certain information, you're probably going to be applying some of the rules from up above to answer this AP-ish style question. And we'll go over this in class when I see you next, okay? So now let's get right to the good stuff here. In order to derive trig functions, okay, find the derivatives, we need 2 important limits to assist us. And these limits, we actually both know the limits for. The first one, we better sure know, right? This is that world famous limit. Limit as h goes to 0 of sine h over h. According to the sandwich theorem, we have proved that that is equal to 1. And that might be something that we need as a reference point. Now, this one's not as obvious. Limit as h goes to 0 of cos h minus 1 over h. But I believe in our notes, as part of a warm-up one day, I did this one with you. So do you remember what the trick is here? Because you're going to get 0 over 0, but to fix it, you can multiply by the conjugate, cosine h plus 1 on the top bottom, right? I think it's probably worth our time to review this limit because it has some really good trig laws and trig properties that are useful here. So when I multiply those conjugates on the top, you get cos squared h minus 1. The bottom is h times cosine h plus 1. So then from there, you're going to wind up hopefully recognizing that if sine squared plus cosine squared equals 1, this isn't quite sine squared, but it is equal to negative sine squared. Okay, if you factor a negative from that, you would get 1 minus cosine squared, which is sine squared. So that's what we've got on the top. Okay, denominator is the same. And the whole goal when evaluating trig limits is to maybe start recognizing some things that you can separate that we know the limits for. You know, if we know that limit as h goes to 0 for sine h over h is 1, at this point, we can do some of that separation. Maybe I'll go ahead and write this as negative sine h over h times, well, I still have another sine h over here. And we'll leave the cosine of h plus 1 below it. Well, if I take the limit of the product, it is equal to the product of the limits. Not quite the same for derivatives, but in this case, this one is going to go to, well, the negative outside would make this a negative 1 now. When I plug in 0 here, sine of 0 in the numerator is 0. The denominator technically is 2, right? Cosine of 0 is 1 plus 1 is 2. And then this time 0 is 0. Okay. So with all that being said, at least it has a limit that exists. It's not undefined or does not exist there. Okay. But these are going to be important limits for what we're about to do in a moment here, which is find the derivative of y equals sine x. Okay. So we're going to use that limit definition in order to determine sine's derivative, it's the limit as h goes to 0 of f of x plus h, so that's sine of x plus h, minus f of x over h. Okay. So in order to evaluate this limit, the first thing that we have to do is take sine of x plus h and expand it using the sum identity for sine. So the limit as h goes to 0 of, I always like a good chant here, sine, cosine, cosine, sine. I'm sure you've had a teacher chant that at one point in your life. All right, so this would be sine x cosine h plus cosine x sine h, and then minus sine x at the end, all over h. Okay, so at this stage in the game, I'm going to do a little bit of selective grouping. Okay, I'm going to group this sine x cos h with the negative sine x at the end. Okay, because what I know about those two terms is that they have a sine x in common. And if you look at the remaining term, I'm going to wind up separating that from the pack. We've got a sine h that maybe will be over h. I like that. So the limit as h goes to 0 of, I'm going to take a sine out of there. So that's going to be sine x times cos h minus 1. I'm going to put that over h. Plus, then over here, I'm going to do cos x times sine h over h. And then I want you to think about, can we take that limit as h goes to 0 at this point and be able to evaluate and figure out the derivative of sine x? And the answer is yes, right? Think about this piece right here. What's going to be the limit as h goes to 0? Well, we just proved that up above, that that is, in fact, 0. So there's going to be sine x times 0 plus, there's my world-famous limit on this side. Limit as h goes to 0, that is 1. So it's cos x times 1. So lo and behold, the derivative of sine x is cosine x. How amazing is that? For sine x is cosine x. Pretty fantastic. I want you to see if you can on your own confirm using the calculator that that makes sense. But we're actually going to use the calculator in the next problem to find the derivative of cosine. So if the derivative of sine is cos, what do you think about the derivative of cos? Is it sine? I don't know. Let's find out. Okay, let's do it graphically though, just to kind of save us some time. Of course, there is algebraic ways of doing this. But if you go to y equals, make sure you're back into function mode here. So what we're going to enter is enter our function cosine x into y1. And then in y2, we're going to do some n-derive to graph the derivative of this function. And hopefully based on that graph, we can tell what the derivative is. And we're going to do this for all values of x. Okay. Now, I guess you actually don't really need this in y1, but it's nice to, as kind of comparison purposes, to see what's going on there. And by the way, if you don't want to retype in cosine x there, you can certainly just enter this as y1. Okay. All right, so in y1, we've got cosine x. In y2, I'm going to do n-derive, math 8. Okay, so find the derivative of what I have in y1. If you want to do alpha trace, we can get y1 pretty quickly. For all x values, we'll graph the derivative. And I don't know, we better be in radian mode to do this, otherwise we're going to get some wacky things. Should have probably zoom 6 this, but here we go. We're seeing what's happening here. Blue is cosine x. Red is the derivative of cosine x. I think it's actually pretty nice if you just look at the left side here, okay? So that looks pretty cosine-ish to me. If I look at the blue graph, what is that red graph? To me, it's looking like upside down sine. At least I hope that's what it's looking like to you. So the derivative of cos x is in fact negative sine x. So not quite sine x, but pretty closely related. Negative sine x is the derivative of cos. All right, these are two that we use very commonly. In fact, we can get practice with them right away in these examples below. I'll do number 1 with you and let you guys try number 2. We'll go over it tomorrow. But make sure we're applying the appropriate rule here, right? So if I want to find the derivative of x over sine x, we just have to make sure that we apply the quotient rule. Okay, low d high minus high d low over low squared. So the derivative here would be low d high, well, the derivative of the top is 1, minus high d low, derivative of the bottom is cosine x over low squared. So just with some quick simplifying on the top, we get sine x minus x cosine x over sine squared. And to be honest, I mean, this is a correct answer. One thing I'll just encourage you to think about is that on a test or quiz, you may find that this is not an answer that's listed anywhere. Because you can maybe do some separating here and develop some other trig relationships that we know. So for example, if I do sine x over sine squared and separate the fraction, and then maybe make this x cos x over sine squared, you know, what would this break down to? This would be 1 over sine x, better known as cosecant x. Over here, you could actually separate this into cosine over sine times another 1 over sine, right? You still have sine squared down there, but cos over sine is cotangent, 1 over sine is cosecant again. So maybe the multiple choice says cosecant x minus x, this is cotangent x, cosecant x. Or maybe it's even fancier than that because these both have cosecant in them. So maybe cosecant is factored out as a GCF and you get 1 minus x cotangent x. So I think at each step along the process, you know, I guess I find the derivative using quotient rule, check to see if that's an answer. But if I'm looking at the multiple choice and I see a lot of cosecants and cotangents, well, then I'm thinking, well, hey, let's split this up and use some of the reciprocal and quotient identities that we know to make replacements here, okay? So make sure that we're making those considerations. You know, I know that was kind of a lot of trig thrown your way, but we have to have a super solid trig foundation if we want to be successful with trig derivatives and other things that we get to this year, all right? So you'll try number 2. Let's get to the derivatives of the other ones. What about tangents? Derivative of tan x. How can I develop the derivative of tan x? Well, I bet you're shouting from your homes right now, do the derivative of sine x over cosine x, right? Write it as that quotient identity. And we know the rule for finding the derivative of a quotient. We also know the derivative of sine and cos. So we're going to do low d high minus high d low over low squared. Okay, low d high, derivative of the top is cos, minus high d low. Derivative of the bottom is negative sine x, so be careful there, over low squared. That would just be cos squared. Okay, so let's simplify it from here then. The top becomes cos times cos, which is cos squared. Negative sine x times negative sine x is plus sine squared over the denominator cos squared. And you could probably do some separation to figure out what's going on here, but why don't we recall that this is a Pythagorean identity, right? It's going to be the easiest scenario. Cos squared plus sine squared is 1 over cos squared, and 1 over cos squared might be better known as secant squared. So check that out. The derivative of tan, to start, is secant squared. Pretty awesome. And now that you start to get used to the hang of this, I mean, everything else can be expressed in terms of the functions sine and cos. If I ask you to find the derivative of cotangent, you can do one of two things. You can find the derivative of 1 over tan using a reciprocal identity, or if you liked what we did in the last step, you would just find the derivative of cosine over sine. And just to kind of save us some time today, I'll write that the derivative of cotangent is equal to negative cosecant squared. Okay, so the derivative of tan with secant squared, the derivative of cotangent is negative cosecant squared. All right, a couple others. Secant, derivative of 1 over cos would get me there. If you use the quotient rule there to develop the rule for the derivative of secant, the derivative of secant is, interestingly enough, secant tangent, sectan. And finally, there are some nice patterns happening here. So I wrote that at the bottom. There's a special pattern among trig derivatives. And maybe you've caught on to that. So if you think about derivative of sine is cos, derivative of cos is negative sine. The derivative of tan is secant squared. The derivative of cotangent is negative cosecant squared. So the relationship among the derivatives has something to do with the relationship among the original functions. And it's maybe a property that we're not as familiar and solid with in terms of our trig identities. But I'll tell you that if you do the derivative of 1 over sine, or wherever you wish to develop this, you're going to wind up getting that the derivative of cosecant is negative cosecant cotangent. So compare these last two answers. Notice how in each case we get like 1 positive, 1 negative, right? Same thing happened up here. And what's the relationship with secant squared and cosecant squared? What's the relationship with sectan and cosecant cotangent? Do we know that special pattern? Tell me tomorrow what you think this special relationship is. Okay, because knowing that special relationship, I think, is really helpful in terms of quickly determining, without deriving it every time, what that derivative is. You're going to want to memorize these for sure. Okay, you'll do trig derivatives enough that we'll definitely want them off the top of our heads. Okay, moving on to the back page here. Find the equation of the line perpendicular to the tangent line. Y equals x sine x at x equals 4. All right, perpendicular, hopefully remembering that from the other day is called the normal line. So we want to find the derivative, and then we'll go ahead and find the slope, and then perpendicular slope from there. All right, so y prime in this case, we just have to apply the product rule, right? So the derivative of the first times the second plus the derivative of the second, which is just cosine x, times the first. So we can clean this up a little bit and say that y prime is sine x plus, let's pull the x out front, x cosine x. All right. So then if I ask you to find these equation of the perpendicular line, let's find the equation of the tangent line by substituting in 4 for x. So it's sine of 4 plus 4 times cos of 4. Okay, please make sure that you're in radian mode still, right? Okay, we're not talking about 4 degrees here, 4 radians, which is, a little bit bigger than pi. So it's somewhere in quadrant 3 if we're talking about that angle. And if you're in radian mode, just quickly on the calculator, you should get y prime of 4 is negative 3.371. So then to get the equation of the tangent line, remember we only know it's at x equals 4. So we'd have to plug that into the function to figure out the y value. 4 sine 4 in radians gives you a y value of 3.027. So now that I have the coordinate point to 3 decimal place accuracy, this is the slope of the tangent line. Make sure you get that perpendicular slope. So the final answer would be y minus 3.027 equals perpendicular slope, right? Negative reciprocal 1 over 3.371 times x minus 4. Okay, and just leave that in point slope form. Really quickly at the end of the lesson, we're talking about a quick application here. Simple harmonic motion. Again, this is getting a little physicsy here. It says the motion of a weight bobbing up and down on the end of a spring is simple harmonic motion. And then this example describes a case in which there are no opposing forces like air friction. That just makes our lives a lot easier in this class. So a weight bobbing hanging from a spring is compressed 5 units above rest position and released at time t equals 0 to bob up and down. So what are its velocity and acceleration at time t? We know velocity, the derivative of position. We know acceleration, derivative of velocity, right? And now that we know trig derivatives, we can actually answer this question. So if we know that s of t equals 5 cos t, we should know that v of t is equal to s prime of t. Okay, derivative of cos, remember, is just negative sign. So the velocity would be negative 5 sine t. And then finally, the acceleration is the second derivative of position, or just the derivative of velocity, which in this case would be derivative of sine, which is cos. Carry that coefficient out front, negative 5 cos t. All right, so actually a pretty quick and easy application once we have a good solid foundation with trig derivatives. All right, much more to come with trig derivatives, and we'll fill in all the missing pieces that we left out today next time I see you.